Hi, welcome back. Last time we talked about one way to define a line in in n dimensions as a linear interpolation between 2 points. Today we're going to talk about a couple other ways to define lines. So let's go back and remember how we talked about lines in 2 dimensions. Um, think about when you were writing the equation of a line in 2 dimensions, what did you do? Well, you probably used one of two different methods, right? So one way is slope-intercept. You're probably thinking y equals mx plus b, right? If you know the slope, if you know the y-intercept, you can then write the equation of a line. And you should look at this equation, you see y equals, right? This is writing y as a function of x. Um, Another way you can get the equation of a line is if you use the point-slope form. So if you have a point, y naught x naught, or x naught y naught, and you have the slope of the line, so we have some point on the line, x naught y naught, and you know what the slope is. I don't know why I drew a vector there. You have your line, you have your point, x naught y naught, and you have your slope, m. Then you can write down y minus y naught equals m times x minus x naught. So we're going to create, so what the key point there is, if you have a point and a direction, you know the equation of the line. And again, this is a function y as a function of x. So now we're going to do this and take this into vector land. So what does it mean to go into vector land? Well, we are now, maybe we're in three coordinates, maybe we're in 2 coordinates, but what we have is we have our line, and what we're talking about is having some line. This is in 3D, and a line is perfectly well defined if you have a point and you have the direction in which it goes from there. So we need this point x naught, y naught, z naught, and we need the vector in which direction you're going. And we're going to call that A, B, C. So if you have x naught, y naught, z naught, and you have that vector ABC, then you can write down the equation of any point on the line, the equation of any point on that line. So I'm going to actually redraw this a little bit differently. So what I'm going to do is I'm going to draw this where we can write a vector equation. Right? So before we were writing this point that in 3 space we have the point x naught, y naught, z naught. But we can also think of this as a vector. We can think of this as a vector from the origin, right, 0, 0, 0, to x naught, y naught, z naught, and now it's a vector, and this vector is x naught, y naught, z naught as a vector. And so now we have this vector, and if we look at the line, the vector A, the slope, this vector, the direction vector, ABC, then what we can do is we can add different multiples of this vector. We can say, let's add a tiny bit of this vector, a little bit more of this vector, a little bit more of this vector, or maybe we add a negative amount of this vector, we add a more negative amount of this vector, even more negative amount of this vector, and as we do that, we trace out a line in 3 dimensions. And so if you look at this, what this here represents, x, y, z, this represents the position of what happens when we add x naught, y naught, z naught, plus any multiple, this is any scalar multiple, of our direction vector. So think about starting at any point and then moving some amount in the direction ABC, and that some amount can be a positive amount, but it could also be a negative amount. And if we do that, then we stay on the same line, and this xyz gives us the value of any point that's on that line. It's a vector, but it can also be interpreted as a set of coordinates, because we could say, well, what's the vector that starts at 0, 0, 0? The vector that starts at 0, 0, 0 and ends at x, y, z is indeed the coordinates x, y, z. All right, so remember, if we have this equation that's giving us what the x, y, z coordinates are, really we can turn that into a set of parametric equations, where we have if we add this coordinate with this coordinate, TA, we add this coordinate with this coordinate, TB, and this coordinate with this coordinate, TC, then that's going to give us the coordinates x of t, y of t, and z of t as you move along that curve. All right, and so this, when we're talking about what a line looks like in 3 dimensions, it's going to have this form where you have x of t is a x naught, so this we can read off the coordinates of a point on the line from x naught, y naught, z naught, and we can read off the direction of the line by reading off the coefficients of t. And this same format also works to give the parametric equations of a line in 2 dimensions. So just like it worked in 3 dimensions, it also works in 2 dimensions, and it can work in n dimensions as well. All right, so this is a really important idea, and let's just repeat it again, that if you have an equation of a line, if you have the equation of a line, you can read off the direction that the line goes in, so the vector parallel to the line, from the coefficients of the t's of this parameter, a, b, c. That's our vector. That's the direction of the line. All right, and so now that we have 2 different ways to think about our lines, maybe let's see this occur as in the other way that we talked about. Remember last time we talked about if we have a line that goes through x naught, y naught, z naught, and through x1, y1, z1, then we can write down an equation of the line that goes between them, and we write it down this way. We write x of t is equal to 1 minus t times x naught plus t times x1. X or y of t is equal to 1 minus t times y naught plus t times y1. And then z of t is equal to 1 minus t of z naught plus t times z1. All right, and so what's the direction between x naught, y naught, z naught, and x1, y1, z1? Well, it's x1 minus x naught, y1 minus y naught, z1 minus z naught. So if we were to take this equation and rewrite it as 1 times x0 minus t times x0 plus t times x1, y0, so here I'm distributing the 1 minus t, y0 minus t times y0 plus t times y1, and this is equal to z0 minus t times z0 plus t times z0. If we read off those equations, what do we get? We get, I'll just move up here, we get x0 plus t times x1 minus x0. We get y0 plus t times y1 minus y0. And we get z0, z0, plus t times z1 minus z0, which is exactly the same equation, x0 plus a times t, y0 plus b times t, and z0 plus b plus c times t. All right, so there's our equations of lines, and it matches exactly with our line that we got from a linear interpolation. All right, this seems like a good place to pause, and we will start up again soon. All right, thanks.